All right, good morning to our U.S. participants, or good afternoon to East Coast, and good evening to our Indian colleagues that might be joining us. Today, we have a presentation on Nano-Grid participation in the wholesale energy and reserve markets, challenges and opportunities. Our presenter is Mohammad Khoshjahan.
Correct.
And a little bit about Mohammad. He is a graduate student member of IEEE and is pursuing his PhD in the Department of Electrical and Computer Engineering at Texas A&M. His research interests include power grid management and operation, smart grids, power system flexibility, electricity market design, and asset management. He's a recipient of the 2021 Texas A&M Energy Institute Graduate Fellowship and the 2019, 21, and 22 IEEE, I think I missed some, chair of the IEEE Texas Power and Energy Conference and was chair in 2021. So we're going to turn it over to Mohammad to talk. For anybody, please put any questions in the chat, but we'll also open it up to at the end for discussion. And Mohammad is working with Mladen Kazanovic at Texas A&M. So Mohammad.
Thank you, Dr. Schultz. Hello, everyone. Welcome to this webinar. Today, I will be talking about the participation of DERs and Nano-Grids in the wholesale markets with the aim to procure trade energy and procure ancillary services. I will be talking about the opportunities and profitability of DERs in this framework and the challenges they may face. DERs in general can bring many advantages to the power grid, such as reduction in the customer bills, which is nice, improvement in the grid flexibility, resilience, and reliability, reduction in the carbon footprint, and more technology innovation. One way that they can be more profitable and attract more investment in them is through participation in the wholesale market and offering ancillary services there. However, this framework faces so many challenges, such as the uncertainty in the DER resources, the probability of outages in the distribution grid that is the means, the physical means that these DERs for the DER energy transactions, and other challenges such as cybersecurity and their visibility to the wholesale market operators. All these challenges together call for an informed bidding strategy models that assure certain profitability of DERs. The type of DER that we are most interested in is called Nano-Grid or distributed prosumer. A Nano-Grid is a residential or commercial building equipped with a rooftop solar panel, fixed battery energy storage like a Tesla block, electric vehicle chargers, and these chargers can be bidirectional or unidirectional, and controllable electric loads. Controllable electric loads are like the home thermostat or laundry or dishwashing machine. Nano-Grids can be implemented in larger scales. They again can lower the electricity bill for the customers, improve the grid flexibility, and more innovation in the power grid industry. We can benefit from the Nano-Grids in different modes of operation. The first one is their participation through aggregation in the wholesale market. Second one is by providing backup support services to the distribution grid, or participation in local or retail markets. And the third one is participating in peer-to-peer energy trading schemes. For the purpose of this presentation, I will only focus on option one, which is their participation in the wholesale market. In fact, this option is also backed by the FERC Order 2222, which mandates the wholesale market operators across the US to enable participation of DER aggregators in the wholesale markets and of the procurement of ancillary services by them. These Nano-Grids, they are relatively small agents. Their power range is between 5 to 10 kilowatts. However, many markets require a minimum capacity such as 100 kilowatts for the California ISO or 500 kilowatts for the ERCOT. And hence, they need a mediator between themselves and the wholesale market, which is called aggregator. Aggregator is responsible for aggregating the demand of nanogrids and participating in the wholesale market and controlling the energy resources of these nanogrids to comply with the wholesale market results. The wholesale market products across the US are listed on the table above. The first one is energy, which is procured to meet the demand. Next is frequency regulation, which is procured to maintain the frequency to 60 Hertz in the US and in most of other countries to 50 Hertz. For this product, the resource needs to be equipped with automatic generation control. The next two are spinning and non-spinning reserve. Both of them are majorly procured to respond to contingencies such as outages in the transmission or generation level. For the spinning reserve, the resource should be already synchronized to the grid, whereas for the non-spinning reserve, the resource must be able to connect and synchronize to the grid and deliver the ancillary service in a pre-specified time limit. The next one is flexi-RAM, or also called RAM capability. Is procured to improve the grid flexibility, which is defined as the ability of the supply to follow the demand. And for this product, the resource needs to be dispatchable. The next one is demand response, which is procured to improve the system adequacy, and the resources should be equipped with the demand response control systems. Last but not least, we have the capacity market, which is procured to ensure the long-term reliability, for example, 3 years in PJM. And the market participant needs to assure the market operator that it has the capacity, it will have the capacity available in the future. The availability of each of these market products in the wholesale markets across the US is given in the bottom table. Energy, frequency regulation, spinning reserve, non-spinning reserve, and demand response are common among all of them. Flexi-RAM or RAM capability for now is only implemented in California ISO and MISO. However, there are some researches in ISO New England and New York ISO to implement this product. And the capacity market for now is only implemented in PJM, ISO New England, and New York ISO. This slide shows the interactions between the ISO, aggregator, and nanogrids. The wholesale market has different processes, but the three major ones are day-ahead market, real-time or hour-ahead market, and real-time dispatch. At first, the aggregator needs to participate in the day-ahead market based on the uncertainties in the nanogrid resources. The aggregator runs its own self-scheduling optimization. The outcome of this optimization are the desired energy and ancillary services that the aggregator wants to get rewarded. It submits the bid to the ISO. The ISO gathers all the bids from all the market participants. Then it runs its own security constraint unit commitment and clears the market. All the energy and ancillary service rewards are binding. Next, it goes to the real-time market or hour-ahead market. Again, the aggregator based on the current status of the nanogrids and its forecast of the uncertainties in the Nano-Grid resources runs its self-scheduling optimization, again submits the bid to the wholesale market. The market operator clears the market, and all the energy and rewarded ancillary services are binding. Next, it goes to the real-time dispatch, where the aggregator doesn't submit any bids anymore, and the ISO sends the dispatch signals to the aggregator. The aggregator, based on the current status of Nano-Grid resources, controls them to comply with the dispatch results. As I said, there are so many sources of uncertainty that the aggregator needs to manage. One is the electric load, PV generation, electric vehicle, arrival time, departure time, and initial state of charge, market prices, and the ambient temperature that affects the thermal load of the buildings. And the other one is the risk of outages in the distribution feeders. All these uncertainties together call for a stochastic optimization model that is able to tackle these uncertainties. The first top five, they can be modeled using by fitting probability distribution functions to the historical data. In fact, the paper that I cited at the bottom of this slide shows how we model them. But the last one, the probability of outages in the distribution system, needs a little bit more complicated work that I will be explaining later. Uh, just remember, these nanogrids, they are connected to the grid through, they will deliver energy and ancillary services to the transmission level through distribution system. And if outages occur in the distribution system, so many of these nanogrids will be disconnected. When they are disconnected, they are not mandated to deliver the ancillary service anymore because it wasn't their fault that they are not connected to the grid. But during this time of disconnection, they usually use the energy stored in their battery, fixed battery, and electric vehicles battery to supply their load. And when after a few hours they are connected back to the grid, they are already distorted from their optimal operating point. And at that point, they might not be able to deliver that ancillary service, which will be penalized by the ISO. However, this is work done by a colleague of mine. By using the historical weather data and the historical outage data in the distribution grid, we can train machine learning algorithms such as decision tree that, based on the weather forecast for a certain time in the future, it can predict the probability of outages in the distribution feeders. We define the risk as the hazard times vulnerability is a conditional probability. Hazard means what is the probability that an adverse weather occurs at that time, and vulnerability says if that adverse weather occurs, what is the probability of outage in the distribution feeders. This algorithm outputs risk maps such as the one shown on the right. The one at the top shows a low risk map, which means the weather forecast was showing a nice weather and the risk of outages in the distribution grid were low. Whereas the bottom one shows probably a harsh weather forecast, such as a storm, and based on that, the risk of outages in the distribution grid were higher. To recap everything I've said so far, we have this ISO or wholesale market operator that is responsible for the transmission level. Then we have this distribution grid, which is maintained by the distribution utility. And we have these nanogrids that are connected to the laterals of the distribution grid that are managed by the aggregator. We assume that the distribution utility, based on the machine learning algorithm that I talked about, can give the a state of risk of the distribution feeders to the aggregator. Now the aggregator knows that at each hour of the next day, with what probability each nanogrid will be disconnected. Based on this information and the other uncertainties that are modeled in the nanogrid resources, the aggregator participates in the wholesale market and gets the desired energy and ancillary service rewarded. For the optimization models, we developed two bidding strategy models for the aggregator, one for the day-ahead market and one for the real-time market. For the day-ahead market, we developed a risk-averse 2SA scenario-based optimization model that uses the well-known conditional value at risk measure, CVAR, to manage the risk in the aggregator profitability. For the real-time market participation, we developed a deterministic model and developed its robust counterpart, and we use the interval plus polyhedral uncertainty sets to manage the price real-time price uncertainties. This bidding strategy was for the connected nanogrids, but when a nanogrid is disconnected, it should be able to, during the time of outage, it should manage its resources optimally, that when it connects back to the grid, it's not that much distorted from its optimal operating point. For this purpose, when the nanogrid is disconnected, at first it automatically delays all the deferrable loads for later times, such as laundry or dishwashing machine. Then decreases the thermal load to its minimum level. We assume that the building occupants can set their minimum and maximum temperature, comfortable temperature ranges. And now, if the remaining load is greater than the PV generation, we need the energy stored in the battery and the electric vehicle to supply it. At first, we start with discharging the fixed battery storage. And if more load is remaining and we have the electric vehicles connected and plugged in, we start discharging the EVs to supply it. And if any more load is still remaining, well, we couldn't supply them. It's called it will be energy not supplied. However, in other case, if the PV generation is more than the remaining load, such as during the day when the building occupants are not home, and we have high PV generation. At first, the PV energy will be used to charge the electric vehicles if they are plugged in. And if more PV generation remains, it will charge the battery. If again more remains, which is unlikely, it will be used to turn the AC thermostat back to the normal level. And if more PV generation remains, it will be used to supply the deferrable load. And still, if we have more PV generation, it will be spilled. We couldn't store it anymore. The reason that we first discharge the battery, then electric vehicles, and we first charge the electric vehicle, then the battery, is that the electric vehicle is used by the building occupants to run errands, travel, etc. And it's more important for them than the energy stored in the battery. Okay, I'm trying to go to the next. Okay. For the case study, we considered an aggregator responsible for 50 nanogrids, 40 residential buildings, and 10 commercial buildings, all together with 150 electric vehicles. We considered the participation of the aggregator in the energy spinning reserve and flexi-RAM markets. We consider two cases, one without participation in the flexi-RAM and two with participation in the flexi-RAM market. The reason was that all the other ancillary services are well explored, but FlexiRAM is almost a more new product, and it's not well explored in the literature. The energy trace, procured reserve, and FlexiRAM in these two cases is shown on the figures on the right. Procurement of the FlexiRAM that didn't impact the energy trading that much. However, procurement of FlexiRAM decreased the procurement of the spinning reserve, because at the end, these Nano-Grids have a certain level of ramp up and ramp down capacities that should be divided into procuring spinning reserve and FlexiRAM. In terms of cost and profits, the cost and the energy cost and the profit from spinning reserve by participation in the day-ahead market is shown on the figure above. As I said, we use the conditional value at risk measure to tackle the uncertainties. It has two adjustable parameters. One is the confidence level that we set to 0.95, and the other one is the risk parameter that we increase from 0 to 1. As we increase the risk parameter, we are taking more conservative approaches. For the energy cost, if you compare the black curve and the blue curve, they are almost similar for both cases, with and without procurement of FlexiRAM. The reason is that the energy cost is much higher than the profit from spinning reserve and FlexiRAM, and the aggregator at first tries to minimize its energy cost. For the spinning reserve, as we increase the risk parameter, the value decreases. However, we can see that the profit from spinning reserve, when we are also procuring FlexiRAM, is less than case one where we are not procuring any FlexiRAM. For the participation in the real-time market, the profit from FlexiRAM and energy costs are shown in the bottom figure. We have two adjustment parameters here for the uncertainty sets. One is for the box uncertainty set, the other one is for the polyhedral uncertainty set. For the different values of these two parameters, the profit and the cost are shown in the bottom figure. Increase in the in these parameters means more conservative approach, which lead to reduction in the profit from FlexiRAM and less cost in the energy cost. That is obtained by mitigating the impacts of the real-time price forecast uncertainties. Now, to consider the risk of outages in the distribution grid, we considered a distribution grid with 10 feeders with 50 nanogrids connected to each of them. The state of risk for each feeder for the next 24 hours is shown in the figure on the right. As it shows, we have a harsh weather from hour 1 to 5, hour 10, and hour 19 to 21. The figure above, the dotted blue and red curves, they show the available ramp up and ramp down capacities if there were no outages in the distribution system. However, the kind of pale blue and red curve, they show the actual available ramp up and ramp down capacities that are different from the total values because of outages in distribution grid. It shows the importance of considering this probability of the outages in the distribution grid, because if the aggregator doesn't consider that, it may over-procure ancillary services and be penalized heavily by the ISO. For the resource management algorithm for the disconnected nanogrids, the results of the total load loss and the spilled PV are shown on the bottom figure. If you compare the blue curve and the red one is almost zero all the time. The blue curve shows the total load, and the red curve shows the load that was not supplied or load loss. Almost we were able to supply all the load of this disconnected nanogrids altogether. There was only 10 kilowatt hours of load loss. For the PV generation, total PV generation is shown in the with the orange lines, whereas the spilled PV generation is shown in the green curve. As you can see, we could absorb some of the PV generation, but not all of it, and the total PV spillage was 2.22 megawatt hours. One reason is that when we have the PV generation is usually during the day when the home occupants are not home and the EVs are not plugged in. So we cannot store much of this PV generation. Most of it will be spilled. Next, we assess the impacts of the repair time of these outages that occur in the distribution grid on the load loss and spilled PV of these nanogrids. As it's expected, the higher the repair time, the higher the load loss and the spilled PV, which shows the importance of fast repair in distribution grids. So far, I talked about the uncertainties in nanogrid resources and risk of outages in the distribution grid and the bidding strategy of the aggregator. Now the topic will be totally different. I will be talking about cybersecurity and visibility. So if anybody has any questions, I will be happy to answer. Otherwise, I will be continuing with these slides.
Yeah, there's one question in the chat. So Ahmed, do you want to, the question is, in the aggregator, are both load controllable and generation PV added together? And the second one is, how do you optimize both load and sources together? And what is the communication type from aggregator to resources?
The aggregator communication type, it can use the home energy management system, HEMS. It can receive the measured signals of these resources, and it can send the command signal, which is the operating point of, for example, battery or the home thermostat or the EV charging or discharging. It says that in aggregator are both load and generation added together. The load has two parts, as I think he mentioned. One is controllable, one is non-controllable. Controllable, as I said, can be thermostat and differable loads. What does it mean by added together? So we can define a net load, which will be the total non-controllable load minus the PV generation. However, the the controllable load will be tackled separately. For the second one, how do you optimize both loads and sources together? Actually, in the paper that I have the citation here, we in detail discussed how this optimization model works. Well, it is stuck. I mean, I'm trying to navigate back. Let's see. Yes, this paper. I mean, I can send it to you if you want to know how it works.
So Mohammad, yeah, just if you have time, then just I can clarify.
Okay.
So the thing is, how do you send? Let's say aggregator is not sitting in my home, right? It is outside.
Right.
So how do you get signal from that aggregator to each home?
Through a home energy management system. It's a small controller that you can install in your home that can send and receive signals.
That is device name, but communication, it means, is it through Wi-Fi, through internet, through power line, those things?
Well, through Wi-Fi.
The internet, maybe. Okay.
Through internet,
and
yes.
Then how about, so for all the devices, you need then one controller, right? So let's say you mentioned your washing machine, your refrigerator, everywhere you need to install a open and let's say close and open some switches for all the devices.
That's a good question. Well, this nanogrid with all these controllable laws, it can be like utopia, like it's a perfect example of nanogrid. All of them have these controllers, and this they can measure their load output. However, a nanogrid can work without many of them. For example, if a nanogrid only has a PV generation and electric vehicle is still a nanogrid. So it depends on the cost, the how much the building occupant wants to invest in this program.
And in this, all those calculations, you only use the money and let's say discharge and charge, right? Let's say only steady state. Do you need for your calculation? Have you ever used any network, all the circuit network, or only I need the load 100 megawatt, source is 10 megawatt, something like that, only plus and minus? Do you also calculate voltage, current, all those things?
Voltage current for the network or for the nanogrid?
Whatever, yeah, everything.
Actually, so these nanoGrids are connected to the distribution grid, and they need to deliver the ancillary services for the transmission grid. So hence the voltage and the line capacities in the distribution grid are important too. Sorry, come again?
I think it was just an echo. Keep going.
Oh, okay. So they're important, and they should be considered in when the aggregator is bidding to the market, because the deliverability of these ancillary services is also limited by the limits in the distribution grid.
Okay, go ahead. Yeah, that's
Okay.
yeah.
So in slide 18, let me go to slide 18. Well, it has a little lag. Why do not BS get charged with extra PV that is going out as spillage? Actually, it gets charged by the extra PV generation, as I explained in the algorithm that I mentioned. However, it has still a certain capacity, and when it fall, it cannot store any more PV generation, and that will be a spill. And the next question, what are the benefits of having nanogrids participate directly in W wholesale market via aggregator? Have you done any comparison with those other participation options? 2 and 3, 2 was participation in the retail market, and the third one was peer-to-peer energy trading schemes relative to the 2222 structure. One fact is that for now, we don't have any actual retail or local markets or peer-to-peer energy trading schemes that is occurring in practice. There are some pilots in some places, I guess, across the Europe. However, participation in the wholesale market is well established. It's real. It's being run in practice, and even FERC Order 2222 backs up this participation of the DERs in the wholesale market. Unfortunately, I have not done any comparison with other two options because for now, they are not realistic cases. I hope I answered this question. So moving forward, I will be talking about the cybersecurity challenges. As we said, these nanogrids, they communicate with the aggregator, distribution utility, and the wholesale market through Internet of Things, which is the regular internet that we use. Is highly vulnerable to cyber attacks. We developed a communication model of a single nanogrid communicating to the aggregator in Mininet Wi-Fi software-defined networking emulator. We ran certain case cyber attack tests using Kali Linux, such as network reconnaissance, ARP spoofing, man in the middle, and denial of service. Unfortunately, all of those tests were run successfully, which means that this communication is highly vulnerable to cyber attacks. However, there are certain simple actions can be taken to improve the cybersecurity, such as not clicking on the links in suspicious emails, not installing the updates or patches, uncertified updates and patches, and using strong passwords. Next, I will be talking about this actually came up when we were talking with Dr. Alex Papalexopoulos about this framework that we were talking about. He said one of the problems that ISOs have is that these nanogrids, they are not visible to them, meaning they cannot trace their sources of energy ancillary services offered by these nanogrids. Hence, we offered implementing the blockchain framework where all these monetary, energy, and ancillary service transactions are securely recorded and can be used to verify the delivery of these ancillary services in later times. I will be giving a little background about the blockchain application in the energy sector. It can be applied in different platforms such as P2P energy trading, local or retail energy markets, and the wholesale market. These processes, this platform, they can go totally on blockchain, or the blockchain can be applied to them partially for certain processes such as billing, communication, grid management, and traceability. And as you can see, our application is the traceability of ancillary services in the wholesale market. I think we don't have that much time to talk about the benefits and challenges of the blockchain. I think everybody knows about them, I mean, because of these cryptocurrencies. So I skip them. Two questions that need to be answered when we are picking the right blockchain framework. One is the privacy, and the other one is the consensus algorithm. For the privacy, the blockchain can go totally public, such as the Ethereum mainnet. It can go totally private, means one owner, or consortium or semi-private, that means multiple entity ownership. Our assessment showed that this consortium fits our application better because permission is required to access the network. It's much faster than the public blockchain. Multiple entities own it. Participants are known. Their real identity is revealed. We can apply the proof of authority consensus algorithm that I will talk about just in a minute. And last but not least, the decentralization is limited here, which is not a bad thing for our application. For the consensus algorithm, there are so many out there. Every day we hear about a new cryptocurrency with a new consensus algorithm, but the major three ones are proof of work, proof of stake, and proof of authority. For the proof of work, the miners or validators, they need sophisticated hardware to compete over solving complicated puzzles, and the one with the best results gets to validate the block. For the proof of stake, the tokens of each miner is at stake, and they are pseudo randomly assigned to verified blocks. Proof of authority is a modification of proof of stake, where instead of their tokens, their reputation is at stake. Our research again showed that proof of authority works the best for our application because first, unlike the proof of authority, we don't need that sophisticated hardware. It's tolerant to 51% attack rule, which means in proof of work, if you have 51% of the computation resources, you can tamper with the blocks. Next one is that the validators are pre-approved and their identity is revealed and their reputation is at stake. It's much faster than the other two, and the number of validators is limited. There's a question in the chat box. Are these Nano-Grids prosumers? Yes, or they are called distributed prosumers. In the Ethereum blockchain, private Ethereum blockchain, each block has this information. The first is the block height, which shows the number of the block in the chain, the public key of the node that the data is sent from, and the public key of the node that data is sent to. Then we have the nonce, which is the number of blocks generated by that specific node. Then we have the input data that are in bytes 32 and hexadecimal. Then is the gas use. Gas is the internal currency of the Ethereum. It shows the gas used for the block validators to reward them. And lastly, we have the transaction hash. The way we developed the blockchain in our case was that we used the Python programming language to generate the blocks and the transactions. It talks to the blockchain through JSON RPC. Web3.py interface enabled us to develop the clients that interact with the blockchain network. We use the Go, Ethereum, or Geth to develop the blockchain, and each node in it is represented by an Ethereum virtual machine, and each Ethereum virtual machine client can generate blocks and download and read the data in the blockchain. We were interested in the transaction speed, so we in the table above it shows the time spent in average to validate 10 blocks per the number versus the number of miners or validators and the computation power or the CPU threads. As you can see, as the CPU threads increases from 4 to 16, we can see higher transaction speed or lower time spent to validate the blocks. But there was no linear relationship between the number of miners and the transaction speed. The case with 3 miners gave us the best results. The bottom two figures, they show the traded energy by the aggregator energy and spinning reserve by the aggregator, and the actual delivered energy and spinning reserve by the aggregator. As you can see, there are some discrepancies in these two curves. They show that this blockchain framework could detect these discrepancies. Now I will be talking about the testbed we are developing in our lab at Texas A&M University. We modeled Nano-Grid with its inverters in Typhoon HIL. We modeled the grid and Nano-Grids without their inverters in the actual distribution grid. Without their inverters in the Opal RT, or we will be using RTDS, and all the computation of the aggregator are done in the cloud server that is connected to the blockchain, Ethereum blockchain, and the data are stored in the blockchain using Solidity programming language smart contracts. To sum up, these Nano-Grids, they could be implemented in large scales and bring out so many advantages to the grid, such as lower carbon footprint, lower bills for the consumers, and the engagement of the end users with the power grid operation. One way they could be profitable and attract more investment was through participation in the wholesale market and offering ancillary services there, which is backed by FERC Order 2222. However, this aggregator bidding in the wholesale market, it has so many challenges. One is the uncertainty in the Nano-Grid resources, risk of outages in the distribution system. I talked about how they can be tackled. And the other challenges are cybersecurity and the visibility of Nano-Grids to the ISO, which can be solved by using a blockchain framework. Thank you, everyone. My presentation is over, and I will be happy to answer your questions.
Okay, we have a couple of questions in the chat here. Can you describe more about the system on slide 28?
Slide 28. About the system, they said?
Ahmed, do you want to clarify?
About the system.
Yeah. So this one, let's say, can you describe a little bit what is in your cloud, what is in OpenRT and those things?
So this Typhoon HIL will be communicating with the OpenRT. In Typhoon HIL, we are modeling a single nanogrid with its inverters, for example, PV inverter, battery inverter, and electric vehicle inverters. Then we will be modeling the distribution grid in the OpenRT or RTDS for now. And in the OpenRT, we have the distribution grid and some nanogrids without their inverters. How they communicate, it will be a real-time simulator, and the aggregate, this nanogrids, they send their power output, PQ output to the grid. The grid, based on running the grid model in time domain, it sends back the voltage to these nanogrids, and they communicate in this way. Next, we have this aggregator that runs all the optimizations that how the nanogrid resources should be operating. It sends this signal to the Typhoon HIL and the nanogrids model in the OpenRT. And all these transactions using the Python language, they will be recorded in the Ethereum, in the Go Ethereum private network that we developed, and using Solidity programming language smart contracts.
So in the cloud server, your aggregator is in cloud server, right?
Yes.
In the cloud server, how many homes you added there?
We can add as many as we want. Right now, we have this nanogrid detailed model of the nanogrid in the Typhoon HIL. We are aiming to model as many as we want in this in the OpenRT.
Okay, and is there any as many as, actually I don't know what does it mean? So
Like
let's
100,
say
if you want number like 100,000.
okay, and then let's say one guy is one place, another guy is another place, of course another place. Is there any, or do you think also that let's say same feeder or same same substation? I don't know. So those things, do you consider also those things? Substation, feeder, and we also need registration, right? In the real application. This is just simulation. Let's say in the real application.
Yes.
And do you know somebody where it is using right now? Any real field application or any pilot project is going on those areas?
For the nanogrids, I know of one it was in the Europe, it was a pilot, but it was for peer-to-peer energy trading schemes, not for their participation in the wholesale market.
All right, thank you.
You're welcome. And
thanks, Mohammad. Sorry. Yeah, I just have a follow-up question here. So it was a great presentation, Mohammad. I need just a few clarification on this test system. So you're saying like Typhoon HIL, right? So do you mean like you're connecting the physical devices like you projected on the slide, like on the right-hand side of it? Yeah, I see the EV battery and the inverter, like a physical component. Do you mean like you are going to connect them, or you just simply modeling them in the software?
Actually, so for this part, actually, another colleague of mine is working on this part precisely.
Okay.
For now, we have developed a model in a single nanogrid in Typhoon HIL, But the main goal, we are having these meetings with NREL on this purpose too, that we connect actual hardware to this testbed. But it's an ongoing discussion.
Yeah, that sounds great. And then the other one I have is like you mentioned distribution grid with Nano-Grids. So you say like each feeder has a 50 nanogrids in your previous simulations. Do you mean like how are you modeling it? Like I know it's a little complicated when you model it in real time. So how did you model all those nanogrids? It's just a simple load plus a simple one generator collectively, or it's something like what is the procedure you're following here?
This is one of the parts of the ongoing discussions. For now, we have not decided how we are modeling them. It can be as simple as just one generator and one load, but it can be more detailed using their time function and model nanogrids there. For now, it's an ongoing discussion actually.
Okay, thank you, Mohammad.
You're welcome.
No, Mohammad,
Sure.
Mohammad, then you mentioned that only one load and all sorts, but that's I asked the previous question that how do you model or how do you handle both load and source separately? So you cannot add all together. Then how do you go for a load and source separate? Because that's why one of the questions was, do you use load and source separately or something? How do you handle load and source both? Because in your Nano-Grids, some are load, some are source as well, right? Maybe you already answered that the just load is source minus load and then the rest, right?
Hmm.
But you need to know what separately your load and source, right? So you need to model, of course, not model, you have to monitor. By the way, do you also use forecasting there? How do you know the load and source, those things? And how do you participate?
Okay, so there were so many questions here. For modeling, if you mean in the real-time testbed or the bidding strategy of the aggregator. In the bidding strategy of the aggregator, you can define the PV generation as a parameter, the non-controllable load as another parameter, and you can write the energy balance equation, and you can simply tackle those two sources of uncertainties by defining certain scenarios. And when the aggregator is bidding, it's relying on its forecast, and it's relying on the probability distribution functions it has fed to the historical data of load and PV generation. And when it comes to the real time, the aggregator sees the actual load. For this testbed, the real-time testbed, we haven't modeled the load yet. We have modeled the PV generation, the fixed battery, and electric vehicle charger. However, I don't think modeling, this is a work of actually my colleague. Modeling the load wouldn't be that complicated. And so did I answer your question? There was one more question too, I guess.
Yeah, they're perfect. Thank you. Thank you.
You're welcome. And there's another question. Can you please share details of the Nano-Grid model in your paper? The first paper here, this one.
Okay, thank you.
You're welcome.
All right, Mohammed, I think you did a great job of presenting and answering questions. So
Thank
fast and furious. So one more question was, is there any alliance or standard?
Standard for communications for what? Can you a little bit elaborate on that, Dr.
The
Said?
aggregator.
There's no standard for it because it will be a third party or a private entity. So it will be having contracts with Nano-Grid owners that how much it can control their load and everything. For example, the owner can say, I don't want to have any deferrable loads. I want to have my laundry done as soon as possible. I don't want you to play with
No,
my
I don't mean that, but okay. Thank you. Yeah,
Okay.
let's say for demand response, there are some, there are one is called Open ADR Alliance or something for
Mhm.
standard or some, they have some standard naming and rules and something. So I don't know for aggregator, but okay. Thank you
So
very much.
demand response is a market product. So here's the thing, and the aggregator is an entity. It's like a company that works on that. So there can't be any standards on the aggregator. However, for the ancillary services or the market products that the aggregators wants to procure or participate in, it should comply by the rules of the wholesale market operator, like other market participants.
Okay, perfect. Thank you very much.
You're welcome.
Thank you, Mohammad.
All right, well, and Mohammed, you finished in time, so you get 3 gold stars.
Yeah.
Normally you run over, so you did a great job of pacing your presentation. So thank you so much for sharing, and we appreciate you sharing with us. And thanks everybody for joining us today, and we look forward to seeing you at future webinars. So have a great Thursday.
Thank you.
Thank you.
Bye.